The kNN algorithm is pretty simple. There is really almost no parameters there other than k. One parameter that is somewhat hidden from sight is the distance function. So it's a key component. That's what we use to determine which training examples are nearest to the example, and depending on how you compute those distances, you can get very different performance out of the kNN algorithm. So that's often overlooked, but distance functions are really important in the context of kNN. The most common distance function that you're going to use for numeric attributes is the Euclidean. So that's just your normal Euclidean distance between the points. So you take an attribute value, you subtract them between your testing point and the training point, square it, add it up all over all attributes, and take the square root. So it's a nice function, it's differentiable, it has lots and lots of nice properties, well-studied, spherical. It does have some downsides, though. It is not always optimal for what you're trying to do. But a priori, if you don't know anything about your domain, Euclidean is probably your best choice. If you have categorical data, you can't really use Euclidean distance, but you end up using the Hamming distance. Right? So you basically look at, for a given attribute, were the values equal to each other or not. So if they were not equal, you take a 1. If they were equal, you take a 0, and you add up the number of differences in attributes. But what are your options? What else could you use instead of the Euclidean distance? It turns out that Euclidean distance can be generalized to a Minkowski norm or a p-norm, which looks pretty identical to the Euclidean distance with one difference. Instead of having a square and a square root, you raise the differences to the power p and then take the pth root of it. And then as you vary the p, you will get a whole family of different distance functions that have very different behaviors. So if you set p to 2, of course you get back your good friend Euclidean. If you set p equal to 1, you get Manhattan distance, the block distance, which instead of taking sort of the straight line between the 2 points, it adds up the x components and the y components independently. But interesting things happen when you set p to other values. You can set p to any value. It doesn't have to be 1 or 2. It can be any positive number. When you drive p towards infinity, you get an interesting family of functions that start behaving like a max. Right? Now, you should be able to convince yourself of that, right? So if you take the difference between the attribute values and raise it to a really, really big power, the largest of all the differences across all the attributes will dominate the others. So the whole thing will behave kind of like a max. And a max in logical space, it's kind of like an OR. It's kind of like a disjunction of the attributes. And interestingly, if you drive the p towards 0, you get a function that behaves like a logical AND. And you can see it if you draw contour lines for the p norm in 2 space. So here I have A is my testing instance, B, C, D, E are my training instances. I have 2 different attributes, feature 1 and feature 2, and I'm plotting how far away those attributes are in terms of different distance functions. So the Euclidean, of course, when p is equal to 2, that's your dashed or dotted lines, the contour lines. All the points on the line are the same distance from the testing instance. So for Euclidean distance, points B and C are the same distance away, and point D is a lot further, and point E is even further. But if I take a different p-value, for example, if I set p to 0.7, then an interesting thing happens. C and D are actually the same distance away, and B is a lot closer to A than C. Which is kind of interesting. That starts behaving a little bit more like a conjunction of the differences. So what I mean there is B and C, according to the Euclidean, they're about the same distance away, but there is a fundamental difference between B and C. Right? B is different from A only on the second attribute. C is different on both attribute 1 and attribute 2. Euclidean distance cannot capture that. As far as Euclidean distance is concerned, they're almost identical. But if you set p to a lower value, it will assign a lot more significance to simultaneous deviations of several attribute values, as opposed to a single deviation of one attribute value. So by playing around with P, you get a whole family of distance functions with properties that are very different from the Euclidean distance. And then, of course, for other forms of data, you have very specific distance functions. So if you have histograms, something like KL divergence is appropriate for measuring distance. And if you're working with text, TF-IDF and BM25, for different domains, you will have custom distance functions that make sense for that domain. So if you're using a nearest neighbor algorithm and you want to classify tweets, for example, Euclidean distance is silly. You would never, ever use that. You would use BM25.